In this video, we're solving problem 14.R.075 from the Larson and Edwards Calculus, Early Transcendental Functions text, 7th edition. We're asked to use the indicated change of variables to evaluate the double integral. This is the integral that was given to us. This was the change of variables that was given to us. The first thing I wanted to do was distribute those 1/2 through each of those expressions. So this is another way of representing x and y in terms of u and v. And they were giving us this region R. Now, rather than evaluating the double integral over R, we're going to evaluate an equivalent double integral over the region S, where S is the image of R under a certain transformation, and that transformation is listed right here. So in order to come up with the region S, which is in the UV plane over here, I need to find equations for each of these boundary curves and then write them entirely in terms of u and v. This first equation is pretty simple. I see that my line goes through x equals 2, y equals 2, and it also goes through x equals 3, y equals 3. So x and y are the same, so y must equal x. I believe this one is parallel to that. Just to check, let's see, this is x equals 3, x equals 4, this is y equals 1, and y equals 2. So we go up 1 unit and over 1 unit, so the slope is 1. We are using y equals mx plus b. We've got 1 times x plus a number. If x is 3, y is supposed to be 1, so I think that should be x minus 2. Let's check. When x is 4, 4 minus 2 is 2. That checks out. When x is 3, 3 minus 2 is 1, so that checks out. So those are our first two equations. Y equals x and y equals x minus 2. And we want to do something similar here. We're going from x equals 2, y equals 2 to x equals 3, y equals 1. So we're going down 1 and over 1. So for this line, the slope is -1. And when x equals 2, y equals 2, so if I'm using y equals mx plus b, and I know my slope is -1, I can substitute in 2 for x and y and find that b is equal to 4. So y is equal to -x plus 4 there on this line. And then on this line, I believe it's parallel. Let's check. It doesn't look parallel because my picture is not perfect, but we're still trying to understand what's happening here. We go from x equals 3 to x equals 4, so we're going to the right 1 unit, and y is going from 3 to 2, so we're going down 1 and over 1. So the slope is -1. And then we need to add a b to that. To figure out what b is, I'll do the same thing that we did on that last one. Goes through 3, 3. So when x equals 3, y equals 3. So add 3 to both sides and we find that b is equal to 6 there. So now we want to take each of these boundary equations and transform them into equations in terms of u and v only. Now sometimes this is a little tricky because you have to figure out what u and v ought to be in terms of x and y. But this is not the case in this problem because they actually gave us the transformation. So I know that y is equal to x, and x is this function of u and v, and y is this function of u and v. So I can just set those equal to each other and simplify the equation. So y equals x is equivalent to y, which is this, 1/2 u minus 1/2 v equals x, 1/2 u plus 1/2 v. And we can subtract 1/2 u from both sides, so those will be gone. And then we can add 1/2 v to both sides. And so we'll get 0 equals 1/2 v plus 1/2 v, which is v. So y equals x is equivalent to v equals 0. And y equals x minus 2 is similar. So I have y equals x minus 2. The 1/2 u's are gone when we subtract those from both sides. Let's subtract 1/2 v from both sides. Then we'll have negative v equals -2. So v equals 2. So those are two boundary curves over here for my region S. V equals 0 is like y equals 0. And v equals 2 is kind of like y equals 2. Okay. Now we're going to do something similar with these two curves. Happen to be lines. I think I want to rewrite that as x plus y equals 4. It's the same thing. Now let's replace x with 1/2 u plus 1/2 v, and replace y with 1/2 u minus 1/2 v, and set that equal to 4. Well, the 1/2 v's reduce this time, and now you've got 1/2 u plus 1/2 u, which is u, equals 4. So that's one boundary. And then y equals -x plus 6 corresponds to x plus y equals 6. And as we saw up here, x plus y simplifies to just u. So this is going to be u equals 6. So our region S is bounded by v equals 0, v equals 2, u equals 4, u equals 6. Oops, this is not to scale. That's our region S. So we've got v between 0 and 2, and u between 4 and 6. Okay, so it's always, almost always the first thing I do. So now let's focus on this. We have a double integral over R, and we're trying to use the change of variables to evaluate the double integral. So there are a few things that we need to do. We just did one of them. If this is f of x, y in general, first thing I need to do to write this as a double integral over S in the UV plane is come up with the image of S under the transformation, the image of the region R under the transformation. That's going to be the region S. Then we need to write our original integrand entirely in terms of the new variables u and v. So we need to find whatever x is in terms of u and v, and whatever y is in terms of u and v, excuse me. And we write this integrand in terms of u and v by making a substitution. Now the transformation was given to us this time, so we can just plug those in. It's really simple. And then for the area piece, that is the absolute value of the Jacobian of the transformation times an area piece in the UV plane. So it's du, dv, or vice versa. So we need an integrand and the Jacobian, and we can just substitute everything in and then evaluate the integral. Well, actually, we already know what this is. The integrand is natural log of x plus y, but we saw over here that x plus y simplified to be u. So this is just natural log of u. So that's our new integrand, or our original integrand written in terms of u and v. So you always want to get the original integrand in terms of the new variables. And then we need the Jacobian. So you're going to have partial derivatives of x with respect to u and v in the top row, partial derivatives of y with respect to u and v in the bottom row. And remember what x and y were in terms of u and v. That was 1/2 u plus 1/2 v for x, and y was 1/2 u minus 1/2 v. So the derivatives of x with respect to u and v are 1/2 and 1/2. The derivatives of y with respect to u and v are 1/2 and -1/2 respectively. and then we evaluate the 2 by 2 determinant. So you've got this times this, multiply those fractions straight across, you get -1/4 minus this times this, so it's +1/4. So you have -2/4 or -1/2. We want the absolute value though in the area piece. So the area dx dy actually turns out to be equal to 1/2 of du dv, area in the UV plane. Okay, so we've got all the pieces. This turns out to be natural log of u. This turns out to be absolute value of -1/2, which is 1/2. And we've got bounds for s. We found those earlier. So we just need to evaluate this integral. And then we're done. Using more scratch paper here. I have the integral from 0 to 2 of the integral from 4 to 6. Those are bounds for u. Natural log of u times 1/2. Since those are bounds for u, I integrate with respect to u first, and then I integrate with respect to v. And the 1/2 is a constant, so you can pull it out front. Remember how we do this? We start on the inside and we work our way out. Now, the antiderivative of natural log of u is not 1 over u. The antiderivative of 1 over u is natural log of the absolute value of u. To evaluate this antiderivative, we've got to use integration by parts. Usually we would say u is the logarithmic function and dv is everything else. But I'm already using u and v for something else, so it's going to be kind of hard. I think I'll just use u star and v star. Just remember that the starred u's are not the same as the original u's. So this is just my u and v for integration by parts. So this is my u star. And my dv star is du. Antiderivative of du with respect to u is u plus c. We drop the constant whenever we're doing integration by parts. The derivative of natural log of u is 1 over u times du. Now, according to the integration by parts formula, we multiply straight across. You get u star times v star minus the integral of v star times du star. And again, I'm just using the stars because we already were using u and v for something else. So I've got 1/2 of the integral from 0 to 2 of u star times v star, so that's u natural log of u, minus the integral of v times du. And we're evaluating all of this from u equals 6, or u equals 4 to 6. I'm just going to put that over there just to remind myself. Don't forget your dv. Now, a lot of students make a mistake here. A lot of students want to just say that that's 1/2 u squared and that's natural log of the absolute value of u and multiply them, but you can't do that. That's not how integration works or anti-differentiation works. You have to simplify this first. Turns out the u's reduce and you're just taking the antiderivative of 1. So we end up with u natural log of u minus the antiderivative of 1 with respect to u, which is u, evaluated from u equals 4 to u equals 6. So we have 6 natural log of 6 minus 6 minus this evaluated at u equals 4. 4 natural log of 4 minus 4. Those are all constants, so you can pull those out if you want to. I would distribute that negative. Negative times a negative is a positive. And now we just have, we just have the antiderivative of 1 with respect to v, which is v. And I've got a couple of like terms here. -6 plus 4 is -2. And the antiderivative of 1 with respect to v, which is v, evaluated from v equals 0 to v equals 2. So we're going to have 2 minus 0 there. That's going to reduce with that 1/2 out front. And so we get 6 natural log of 6 minus 4 natural log of 4 minus 2. Now there are infinitely many ways we can write this difference of logarithms with constants out front. I'm just going to leave it this way, but you can write it in one of the equivalent forms using log properties if you want to. Otherwise, we're done.